Hello, Algebra 2. This is day 1 of 7.4 geometric sequences and series. And today we are going to look at how to write a geometric sequence as a function. So sequence is a set of numbers in a particular order or pattern. Each number in a sequence is called the term. The first term of the sequence is denoted a sub 1, the second term a sub 2, so on. You can have a finite sequence or an infinite sequence, where a finite ends and an infinite will just continue without end. Earlier this year, we looked at arithmetic sequences. Arithmetic sequences will develop a pattern where there's a number being added each time. And we could rewrite this as a function. This would be a starting point of 1. And so our function could be y equals 3x plus 1, because we're increasing by 3 each time. Today we're going to look at geometric sequences where there's a common multiplier each time. So we can see here we're timesing by 2 to get to each new term. So I could rewrite this as a function, y equals 2 to the x power. So my first term is a sub 1, 2 to the first power is 2, a sub 2, 2 to the second power is 4, a sub 3, and so on. So we can write these sequences as a function. We've done arithmetic, and this would represent a geometric. In a geometric sequence, each term is determined by multiplying a non-zero constant by the previous term. That constant value is called a common ratio. In our previous example, when I have 2, 4, 8, 16, the common ratio is timesing by 2 each time. Sometimes it can be tricky to find the common ratio. You can take the next term and divide it by the previous term, and that will help you find that common ratio. And below here we have our explicit form for finding a function to represent a geometric sequence. To find a term value, a sub n, we can take the first term, a sub 1 times r, and then to the n minus 1, where n represents the term number you're looking for. A sub n represents the term value of that number. The explicit formula allows you to find any term value at any point in the sequence. And we also have a recursive formula which allows you to find each term in the sequence if you know the previous term. Lastly, you can find missing numbers in a term. So for example, that same sequence, if I have a 2, and then I don't know this middle term, but then I have an 8, to find the missing term in the middle, you can take the square root of the two numbers multiplied together that are on either side of the missing number. So the square root of 2 times 8 is the square root of 16, which equals to 4. So 4 would be my missing number. In some cases, we could have a sequence that flips back and forth from positive to negative. So that value of 4 could be a 4 or a negative 4. We're going to determine whether or not this is a geometric sequence. So we can check each next term and then divide it by the previous term to see what the common ratio is here. So that was 3. If I take 15 divided by 6, that's going to equal 2.5. So this is not a geometric sequence. Next, we're going to find the first 6 terms. We're not going to graph these. So here I start with a -1 and then go to -2. So I can take -2 over -1. That equals 2. -4 divided by -2. That equals 2. So I can see that to get to each new term in my sequence, I'm timesing by 2. So my next 3 terms are going to be -8, -16, and -32. In example 3, Javier wants to eat less chocolate each day. To achieve this, he decides to start with a 50-gram bar of chocolate and eat half of it the first day, then half of what is left of the bar the second day, and so on, eating half each day. If Javier starts on a Monday, what is the mass of the piece of chocolate that he will eat on Friday? So from Monday to Friday would be 5 total terms. So we have a sub 1, a sub 2, a sub 3. And on Monday, he eats half the bar, so he's going to be at 25. On Tuesday, then he eats half again. Then he's at 12.5, 6.25. Then we'd be at 3.125. And then lastly at 1.5625. This method, I'm using a recursive method where if I know the previous term and then each day I'm eating half, so I'm basically timesing each of my previous values by half to get to my next term. And I can recursively find what that 5th term is going to be. A second method is we could use the explicit form. So in the explicit form, we're going to need 2 things. We need to know actually 3 things. We're going to need to know what the first term is. So on that Monday, you'd have 25 grams. Each day he's eating half, so our R is going to be 0.5. And we have an N of 5. So using our recursive formula to find the 5th total term, we would take the first term, 25 times 0.5, and raise that to the 5 minus 1. So recall the recursive formula is going to be a sub n equals a sub 1 times r to the n minus 1. And throwing that into our calculator, we will get the same result of on Friday, he would be at 1.5625 grams left of the chocolate bar. So in each of these cases, I was able to find the amount of chocolate left. So recursively is just going one term by one term. So knowing the first term is 25, we can just find each consecutive terms, or directly going to that 5th term would be using that explicit form. So for a situation like this, only 5 terms, recursive is an okay way to go. But if we needed to find, say, the 30th day or the 50th day, then we would want to use the explicit because it's going to be much more efficient. We're going to write an equation for the nth term using our explicit form. Looking at my first sequence, I can find the r value and see that I'm going to get -3. So I have my a sub 1 is -1, r is going to be -3. And those are the 2 things that I'm going to need to be able to write a explicit form for the nth term value. So we're going to have a sub n equals a sub 1, which is -1, times our common multiplier, which is -3, times, or to the exponent of n minus 1. In part B, I know the 8th term is 5, so going out 8 total terms, I know that that 8th term is going to be 5. But I need to write an explicit form to develop all these, knowing that this r value is 1/2. So using the explicit form, a sub n equals a sub 1 times r to the n minus 1. Since I know I have the 8th term of 5, I can put 5 in for this term value. So there's my a sub 8. And then I don't know what the first term is. I do know what the r value is. It's 1/2. And then I can raise that to the n minus 1. And then doing some algebra, I'll have 5 is equal to a sub 1 times 1/2 to the 7th power which 1/2 to the 7th power is going to equal 1 over 128. And then using the reciprocal of 128, 5 times 128 is going to tell me that 640 is that first term. So this first term is 640, and then 320, and then 160, 80, and so on until I get to that 5. So then writing that as the explicit form, I could have a sub n is equal to 640 times 1/2 raised to the n minus 1. So there would be an explicit form to represent that sequence. Given a formula for a geometric sequence in recursive or explicit, translate it into the other form. So part A is communicating a sub 1 is equal to 5, and then to get to each new term, remember this a sub n minus 1, this means the previous term. And I would take the previous term and multiply that by 1/5. And so my a sub 1 is equal to 5. And then to get to each new term, I would multiply by 1/5. That's going to be my r value. And so then I can write this in explicit because this is currently in recursive form. And I'm going to write it in explicit as a sub n equals 5 times 1/5 to the n minus 1. And so in recursive form, I can find each term one at a time. With the explicit form, I could skip to any term that I want to. Heading to part B, I have a sub n equals 2/3 7 to the n minus 1. This right now is currently an explicit. And from the explicit form, I can see this is my a sub 1, this is my r. And so now writing it in recursive, a sub 1 is equal to 2/3. And then I'm going to take, to get to the next term, I'm going to take that previous term and times it by 7. So this is communicating this right here is take the previous term and multiply by 7. And so recursively will allow you to find each term one by one. So the first term is 2/3, the next term is going to be 14/3, and then the next term, and so on, and keep multiplying that by 7. Lastly, finding geometric means. So geometric means are terms in a geometric sequence that are missing. So when we defined geometric means earlier, if I have a missing term in between, just one missing term in between two numbers, I can use the formula for geometric means is just taking those two terms, timesing them together, and taking the square root, which would tell me that this number is 4, or technically -4. So that's if I just have one number in between two numbers that I'm missing. Here I have 4 geometric means to find, so I'm missing 4 of these numbers. So 243 is my first term. This is my second, third, fourth, fifth, and sixth. So I know that my first term is 243. My last term is 32, which allows me to start looking at the explicit form. The explicit form is a sub n equals a sub 1 times r to the n minus 1. So I do know this a sub 1, so I do know that that's 243. The second thing that I know is that the sixth term is 32. So this 32 is representing the a sub 6. I don't know what the r value is, but I can now take that r value and raise it to the 6 minus 1. And then doing a little algebra, we got 32 is equal to 243 times r to the 5th. I can divide both sides by 243. And I'd end up with r to the 5th is equal to 32 divided by 243. I can raise both sides to the 1/5 power. And I would get r is equal to 2/3. To get to each new term, I'm timesing by 2/3. And doing a little figuring using a calculator or whatnot, we can find that this would be 162, this is 108, this is 72, and this is 40. Another case that we might approach is having 3 missing terms. So I have a first term of 3 and a 243. I can target this middle term by using that geometric mean formula. So that would be 3 times 243. So the square root of 3 times 243 is going to end up being 81. So, excuse me, it's going to end up being 27. That tells me this term is 27. Then if I wanted to find that term, now I can do the square root of 3 times 27, which is going to equal 9. And if I wanted to find that term, I can take the square root of 27 times 243, which is equal to 81. So if I have an odd number of missing terms, I can find that middle term using the geometric mean formula, and then I can find it. Otherwise, if we have an even amount of these geometric means we're looking for, then we can use the explicit form to find what those missing terms are. And we need to know what the R value is. So that wraps up our day 1, and we'll head to our day 2.